Monday afternoon. You can go to the other presentation. I won't feel bad because you can just come to it, then. This is going to be my, I'll get the microphone going here, my trial run, so forgive me. I actually wrote an entire script, so I'll try not to sound like I'm reading from the script, but I didn't want to forget everything because there's a lot to go into this. And you don't need to download the NI mobile app unless you're going. But okay, this presentation is how I solved one of the most difficult problems I ran into when I was developing my first very large LabVIEW object-oriented based application. And I thought it was useful enough to make a kind of a general presentation of this issue, because it does come into play in a lot of other applications and other architectures, not just the one that I use. So that's what I'm trying to do, is share how I solved it, at least. And I'm not saying it's the only way to solve it, but this solution works well for me. It's been deployed for several years now. I built several applications based around this, so I know it works. And I've seen other people's solutions, and what I've found is that often the things they've presented will basically be something like this, but they'll talk too much about the specifics of their situation and less about the general. So I'm trying to be very general here, but I'm happy to answer any questions about the details, why I did it this way, or how my application works if you want, but we can maybe hold that towards the end. Anyway, how many people in here are very familiar with OO programming? Okay. How many just saw Dave's talk? Okay, for those of you who didn't see Dave's talk, I do have a little bit of an introduction here. The other guys can just nap for a little bit. And I'm going to dive right into that right now. So, okay, so what we're talking about here is static links that get formed between classes, and how do we break those links so that we don't end up having these dependencies in our application that we do not want. So I'm going to start with a quick explainer of these OO concepts, at least the ones that I'm going to be talking about later on, so that at least we're speaking the same language. If you don't totally understand those concepts, we can go into it in more detail if you'd like, but hopefully this will be enough so you can see what I'm talking about. And I do have one thing in here that's not 100% accurate, and I realized that watching Dave's presentation, so Dave can call me out on that one, and I'll edit it before NI week. Good luck if you can pick it out. Okay, so the concepts I'm going to be talking about are inheritance, abstract versus concrete classes, the factory pattern, and dependency injection, which probably should have been dependency inversion principle, but anyway. There's both, they're basically the same thing. So, when I got started doing OO, the first thing I did is I read this book. And I highly recommend this book to everybody. It is definitely not written in LabVIEW. All the examples, I believe, are in Java. There might be some in C#, but if I remember correctly, it was mostly Java. So I glanced at them, but the text of the book and the concepts it goes over are very, very useful. This was actually recommended by Stephen Mercer, who's kind of, I guess, the godfather of OO in LabVIEW. He's the person that started really pushing it, and a lot of us have learned from him. Another book that's really useful, and this is for understanding design patterns. You may hear people refer to this as the Gang of Four book. So if, because it's written by these four authors. This is a good one to get an idea of all of the different ways you can apply OO design to your problem. And there's a lot of these stock concepts and solutions that you can then say, oh, I have one of those, or I need to build one of those because that's how my problem looks to me. And learning them and knowing to recognize them is helpful. My mistake was not having read this before. I just went ahead and developed my application, and then I later looked back at it and says, oh, that's a factory pattern. That is, a decorator pattern. I just did it naturally, because I was learning and figuring out, how would I do this best? But had I been armed with this information, I would have been able to jump to those solutions a lot faster. And one more book, and this one covers the solid principles that Dave was referring to. So this is another one that comes highly recommended. Almost every advanced OO LabVIEW developer I've ever met has told me to read this book. So I'm telling you to read it too. All right, enough about the books. Okay, inheritance. So, inheritance allows us to define interfaces for categories of classes, such as a message class. The child class uses the inputs and outputs defined by the parent. Since the child can now travel on the parent's wire, we can use dynamic dispatch to invoke common methods in the child that were defined by the parent. Children can access data defined by the parent without implementing additional code to access it. So this is really the key way that we do, we extend classes and make categories of classes. And so when you're thinking of any kind of a message-based architecture, you're going to have a parent message class that everything's going to inherit from, and then you're going to extend that by adding functionality for each of those that you need to do. And then you're using dynamic dispatch to execute those messages, and you design your system so it doesn't matter what message is being executed, it's a generic solution. So a quick, and I've got some very, very simple demos, but I'm just going to go over these quickly. All right, so we've got a parent class and a child class, and the parent class has a number in its private data, and it includes accessors to read and write that number. Now the child class has a method, and the child's class method has access to the parent's data, and it has access to its own data. So this is essentially what you get with inheritance, is that you get the ability to access the data and the methods that are exposed in the parent's class inside the child. So you're extending it. You're saying, okay, you can do this, and now the child can do that and this. So you're adding the functionality, essentially. So that's the most simple way of explaining what inheritance is, at least in my terms. If anyone has any questions, though, please, at any time, just raise your hand, and I can try to explain anything in more detail. Okay, abstract classes. Okay, abstract classes are parent classes that have no methods. So this is kind of a strange concept, I understand. But basically, this is where you're more or less defining the interface. You're not defining the functionality. So they don't really exist in LabVIEW. Just like constructors don't exist, abstract classes don't really exist. But we kind of have a way of faking them. And the way I define it, or at least when I say we, but personally, the way I define it is the class whose methods must be overridden. So you create this abstract class. You put in the methods in it that you want the children to implement for you, but you have nothing on the block diagram. So just the inputs and outputs exist, they're connected up to the connector pane, but there's nothing behind them. Or maybe there's the template that whatever LabVIEW creates when you generate the method is there. You don't even have to delete it, because the code will never be executed. It must be overridden by the child, which means that the child class must create a method that replaces this method. But because the method exists at the parent level, the interface, the outside code, is going to use these methods to talk to the children, and only these methods. I think I pretty much described all of that. All right, so I got a demo for this as well. Collapse that. So here is an abstract class, and we're going to get back to this one in another one of the demos. But essentially, I've got a method, and if you look at it, the method, it doesn't do anything. Literally, it's just a template code. So this would be the class. It does have private data. Some of that private data is exposed with an accessor so that other methods can call it. Some of it remains private. Value is hanging on me. But it doesn't do anything. So you still have your connector pane, you still have your inputs and outputs. Didn't even bother creating an icon. I shouldn't be creating an icon. But that's what an abstract class would look like. So, so what do you do with that? Well, you need to generate a concrete class to actually implement the what the abstract interface defined. And this is where the actual work gets done. So you will, as I said, you'll be overriding all the methods with real methods or concrete methods. That's why they call it a concrete class. And a concrete class can be statically linked to any other code or classes that call their methods. So if your concrete method has to use through composition or through any other process another class, another type of object in your application, then you're statically linked at that level. So that means that when you load the concrete class in the memory, then you're loading the classes that it's using in the memory. But the abstract class is not linked to those methods. And that's where all this is kind of heading. So keep that in mind, because that's what the presentation is basically about. All right, jump too fast. So let's show a quick example. So here's a concrete class. And this concrete class implements the abstract class above. And again, we have our perform action, but in this case, we take the parent data, the numeric, and we add whatever the input number is to it, and then we save it back, and we also output it. So this is actually doing some work, but it's using the interface of the parent. So the parent defined that interface as something that has a number in and a number out, and here in the concrete class, we still have number in, number out. So there's no change to the connector pane at all, but the code underneath it actually implements what you want to have happen. Does that make sense so far? Okay. I know some of this may be like really, really basic for some people, but for those of you that are not familiar with OO, it's kind of helpful to see the nuts and bolts of it, I guess, a little bit. Okay, the next thing I want to talk a little bit about is what the factory pattern is. This is one of the most common design patterns that I've come across in OO. It seems like everything I write has some kind of a factory pattern somewhere in it. And it's basically how the message handler works in most message-based architectures. So it's a factory that's processing object widgets that come into it. And this dynamic dispatch, which I think has been brought up in almost all the OO presentations today so far, that's what makes that work. So it executes the method for the class that's actually on the wire, not for the class that you specified at design time. So at design time, you're using that abstract class, and you're saying call this abstract method, but at runtime, whatever child class is on the wire, its method is what's really going to happen. So that's what dynamic dispatch does for you. Let's see here. Okay, and I also have a demo of this. Oh, just to make sure it's clear, if anyone here has ever used Actor Framework, I show hands, anyone? 1, 2, 3. Okay. Well, in the Actor Framework, there's a do VI inside of the message object, in the or message class, I should say. That is what gets executed in the message handler. So that's the thing that the factory executes. So a quick demo of factory pattern. Is this big enough up here? I didn't even bother to check to see if my resolution was good or bad. But okay, so I've got a very simple application here. I have one input number and then another number, and then I have an operation and I run it and I get a result. I can change my operation to a different operation and I get the appropriate result. Now the way this is working is the operation is choosing which class to use, whether it's going to use the add class or whether it uses the subtract class. And then it's calling the abstract method here of do that operation. So here's my concrete classes in here, add and subtract, and my abstract class here. And we can see what happens if we double click on this. It tells us, well, what do you want to look at? Do you want to look at your abstract class or your specific one? So if we look at the abstract class, it doesn't do anything. It's just defining the interface. But if we instead say, well, let's look at the subtract one, what does that look like? Well, it's got the exact same interface, but then it actually does the operation. So that's how that works. So you're processing based on your input, which one. So this is again, essentially what dynamic dispatch is. Okay? Is that too simple, or?
Yeah, why do you need all that? Why do you need to have the abstract class?
So,
What's the purpose?
so the idea here is that at design time, you don't know all the messages that you're going to want to send when you're designing this, so you're making this generic message handler, and it's a piece of code that's reused everywhere, basically. And its job is just to say, hey, a message came in on whatever method you use to send messages, queues or whatever, and I need to do something with it. But I'm not, as the developer of this message handler, I have no idea what those messages are going to be. So I'm just going to call the do whatever the message says to do method. And then later on, you can design as many messages as you want, and each message can have a different purpose, and all it has to make sure you have in it is that do method. And then you put the real code there, so that when that message does arrive at this code you designed a long time ago, it will call your specific implementation you want. So that allows you the ability to make something that maybe has 5 messages, and then 3 months later you say, oh, I gotta add 5 more messages to this thing. I don't have to write any new code, I just have to create those new messages. I don't have to redesign the processor. So the thing that runs, the loop that runs and does the work and does, that runs the thread and manages all that, that never changes. You just extend it and extend it as long as you want. You can have hundreds of messages, and you can just keep adding and adding. So it makes a more maintainable, extensible application. And that's kind of why OO is powerful, I guess, at least in my opinion. Any other questions? All right. So the next thing I want to talk about was dependency injection. Okay, this is actually dependency inversion principle, but basically the D in solid, which Dave was mentioning. So we want to design this code that depends on the abstract classes and not those concrete implementations. And that's really what this is getting at. It's allowing us to add functionality at a later date without redesigning that core architecture. So exactly what I was just saying before. I probably should have jumped to this slide to explain that more. So when you execute the code, you're calling that abstract method, you're actually executing that concrete method. And that's what this gives you. So you've built an entire system that's dependent upon this definition instead of this actual implementation. And the definition should never change, and the implementations can change. So Dave had that great example of the changing the gauge. So you've built code that depends on there being a gauge that gives you back a reading. But then there may be a whole lot of code underneath there, whether it's a serial implementation or a real-time embedded implementation or whatever, that actually generates that number. You don't need to care about any of that. That can be added on later, it can be loaded at runtime, doesn't matter. You're dependent, your whole application is dependent upon the interface of a thing that gives me back a number. That's what I need to depend upon. So that's the key benefit of dependency injection. So it's important, though, to provide your application with a way of referencing this concrete implementation that it needs to run. So at runtime, it's going to have to know, okay, what's the real deal here? What's the thing the code I'm actually going to use? And so let me give a little quick demo of this. So this demo doesn't really do much. It just takes one number and increments it. But what's actually happening is at some point early in our application, we're going to initialize our application and we're going to provide the concrete class. So this is composition. So again, that's Dave was talking about composition in his presentation as well. So this class has as its private data this other class. So it's composed of. And then at a later time in our application, we're going to read out the value that was stored here. Now we're injecting this concrete class, but what we read out is the abstract class here, and we call the abstract method. So when this runs, it's going to run the concrete method that we injected here. But this part of your code has no idea that it's that particular method. This can be loaded through an initialization file, can say go load this class off a disk and store it in here. You don't need to know at design time. Here, obviously, I've dropped it on the front panel, so it's known at design time. But at runtime, this can be loaded. So this would be, you might load a set of plugins that you've created for a test system, and you want to make a generic test system, and then you want to have different sets of plugins depending upon the project you're working on. So at runtime, your INI file says, go load this set of plugins, and then when you execute them, you're going to read what you loaded and run them. Maybe it would be helpful if I had the help on here, and I can just kind of show you. So let's see here. Come on. There we go. So you can see this is my concrete class that's stored inside of my app class. And then my app class passes along somewhere into my application, and then I read out the abstract class. So this is the abstract class, but on this wire is traveling this concrete class, because this class is a child of the abstract class. So keep that in mind. Remember we talked about inheritance. So the concrete class inherited from the parent abstract class. And then we call the abstract method, and it's going to run the concrete implementation, which just increments the number. So you see that's how it gets to execute the actual code. Okay. And then one more bonus slide about composition, because it really is important. And again, it's a class that uses another class. Okay, the injected class from the previous demo was stored in the applications class using composition. And we make the abstract class a data member of the application class so we can store the concrete version at runtime. And I basically have a little bit extra to show you here. So just so you can see how it was done, here's the main class, and it has subclass as part of its private data. And I have read and write accessors to read and write the subclass. And then from the main class, I can call the subclass. So here it is, the main class unbundles or reads out the subclass and then executes a method that's in the subclass. So that's basically how you would do simple composition in an application. Again, these are really, really simple versions of these concepts. When you put this into your application, it gets a lot more, fully blown. But just so you can kind of get what's the core idea here is what I'm trying to get at. Okay. Okay. So we're done with. Is there any more questions on this? This is kind of like the primer to make sure you understand what I'm talking about in the rest of the presentation. So is this clear as mud now, or good? Or all right, good. And feel free to stop me at any time. I actually will probably finish early and we have a lot of questions at the end. I'm going to load the next piece here so that I'm ready for it real quick. That's loading. Okay, so message handler. So this is kind of what I was trying to build towards. All right, so message handler is the main component of most message-based architectures. Just like Actor Framework, or I have my own framework that's similar to Actor and similar to a few other ones. But pretty much every framework I've seen has a message handler. And its job is, as it sounds, to listen for messages and execute them in the order that they are received. So there's two main parts to a message. The private data and the public accessors that define the data payload. And these are normally only in the child class. You don't normally have any data methods in your very top level parent of a message. You just, each of your actual messages that you create will have that in there. And then you'll have that public method to execute the message. The do VI in Actor Framework, I believe I call it the execute VI in my framework. But it's basically the thing that the message handler is going to run when it receives the message. Okay. Okay, so this type of message is actually called the command pattern message. And why would you want to do that? Why would you want to tie your data and your execution based on that data together? And there's a lot of people who will disagree with this way of doing things, but it's the way Actor Framework does it, and since I didn't know better when I was designing, I said I'm going to do what they did because they're smart people. And there are very valid reasons for doing it this way. But there are consequences as well, and that's what we're going to be covering here. The best thing about this, in my opinion, is that you get strict type definition of the data. So the sender of the message knows exactly what the data that the message contains is going to be. So you're not sending a variant, you're not sending a string where you've stuck a bunch of things together in it and tried to make it into data. You have exactly the data types that you're going to be using. So you can't accidentally put in unparsable data that the receiver says, I don't know what the heck this is, I can't decode it, or you can't put in the wrong, you can't put a Boolean in and it's expecting a numeric out of the variant on the other end. I've designed systems in the past where I only use variants to pass data around, and that was a runtime problem. Would be if you send the wrong data type as flattened to a variant, and then you undo it, and you suddenly realize it doesn't work, and you get an error, and you don't know why. So avoiding runtime errors is one of the benefits of command pattern. It also allows you to encapsulate your data with the behaviors in a single class. And this actually I think is very helpful. Again, some people disagree, but I like to be able to look at the message and see what is the data that this message utilizes and what is this message going to do? What is its actual actions it's going to take? All in one class, one spot. I don't have to dig around. In systems where you pass only data around, the receiving application is going to have what you might call the caseosaurus, the giant case structure with like 110 layers of cases in it that each say, okay, well, if the data has this command in it, then do this case, and if it has this command, then do this case, and you end up implementing that do VI, that thing that you execute, all of them for every single message, all inside of one receiving method. And it makes that thing very bloated, I think, and difficult to navigate, and you can't say reuse code very easily. Let's say if that message is very common to a lot of other things, and you want to be able to send it to 5 different actors. Well, you can design it so that one message can be reused in multiple actors if you want to. I've done that myself. A good example would be you have a piece of data that comes in, and you have 4 UI panels, and they each want to show that status value in a different way. Well, you can send that message to all 4 of the actors that are running those panels, and they can each interpret it and use it and display it differently. And you don't have to write 4 different messages and have 4 different cases in 4 different VIs to do that. You can write one message. So it's really, really helpful to be able to do that, in my opinion. That's why I like to use it. Also, because of this, when you execute the message, you can access the state data of the actor. So the thing that's receiving this message and actually going to do something about it, the message itself can read the state of your actor because it has access to that, and it can modify that state. So you can read values that are stored in the actor. I probably should have said this originally, but the actor is the independent thread, the independent loop that's running, that's doing something in your program. And you generally have multiple of these running. So one may be running your UI, one may be the processing your test results, one may be monitoring a piece of hardware. They're just independent loops. So they're each based around low message handlers. So being able to access the state of each of those items and being able to modify that state is what the purpose of a message is. When you tell it to stop, it needs to be able to see, well, am I even running first? And if I'm running, then stop. If I'm not running, then no op, or maybe send back a message saying, you know, I'm already stopped. Or maybe I can't stop. I'm in a critical spot, you know. So you might send back a status message saying, trying to stop, for instance. But that's the key thing, is that you can access the state data. Now this is where the problem comes in, because if you are accessing the state data of the actor, the message is now statically linked to the actor that's going to be using that message. And that's where we're going to get to how we break this apart. So here's a real basic app. You have an application, it has a process, the green box being the actor. It has a message. The actor calls the message acts on the actor's data. So this is the most basic actor example I can think of. I'll have a quick little demo of this so you can see what this would look like. If it would load, come on. Everything's taking longer to load today for some reason. So here's my actor, and I can increment my number, and then I can stop it. And the way this works is I construct my architecture here, I create my actor process, I give it a name, I give it a method to receive messages, I tell it to run, and then this is where the loop is, it's running. And just so you can see, that's the thing we saw up on the screen. And then when it exits, I destroy and clean up. So just a real basic application. So the key thing here is, let me go into the messages. So here's the message for incrementing the number. And its job is to, so we take in a generic process, but in this case, so this is the abstract version of an actor. We cast it to this particular actor. So this is the statically linked to my process one actor. That gives me access to the private data of that actor, then the number, and it also gives me a user event that the actor has provided me so that I can drive the UI. I increment the number, I save it back into the private data. So I'm using the state data, I'm reading the state data, I'm writing the state data, and then I'm firing that event so that the UI updates and you see the number incrementing on the screen. It's pretty simple, but again, the key thing to see here is that this message, which this actor receives, requires us to have a static link to the actor so it can do this work, so it can see the data and do something to it. Does that make sense? Okay, cool, good. So, this is the problem. So the message needs an instance of the actor to access the private data. And when you load the message into memory, the actor class gets loaded too, therefore, because it's statically linked. The sender, whoever's going to send you this message, needs an instance of the message class to be able to create it. They need to be able to put the private data in there and then send it off to you so your message handler can receive it. which means the sender loads the message class into memory when the sender is in memory, which loads the actor class into memory. If the actor class also sends messages to other actors, those messages get loaded into memory, which loads their actors' classes into memory, which loads the messages in those actors into memory, and so on and so forth. So what you end up having is that if you load one of these classes, you load everything into memory all at once. Now, this is only really a problem when you're sending your messages between two applications, and that's what we're going to demonstrate next here. Does that make sense, though, why this problem occurs? Because of those static links, because the message needs to be able to not just be the transport of data, but the execution of the data, and therefore it needs to know about the thing that's running it. It needs to have a link to it, and now you've linked together everything. And you didn't really intend to do that. This does not happen, by the way, outside of LabVIEW. This is a LabVIEW-centric OO problem. It's not a problem in other programming languages. All right, so how are we going to break these links? Well, we're going to add an abstract execution class. This is what I like to call it, at least. And so I'm going to tie all these things we've been talking about back together now. This abstract execution class, it requires a method for every message you have. So if you have 10 messages in your system that's going from application 1 to application 2 and back and forth, this class is going to have 10 methods in it.
So
each one of those.
Is from earlier, tying it into how you started this conversation.
Yeah.
This would be like your add and your subtract methods, correct?
Yes, exactly. So if I've got an add message and a subtract message, and they each have a execute or a do in them, then I have to have a method for adding and a method for subtracting in this abstract class. So this is going to be my glue that kind of lets me break these things apart. And I've got a nice slide coming up that'll visualize this better. So this way, the sending application needs the message class and the abstract execution class. So the message class now doesn't call the method that actually links to the actor, like we saw where we had that static link to the actor. That doesn't have anymore. Now the message classes do, it calls the abstract method that we're sticking in this abstract execution class. So the subtract message, its do, calls the abstract subtract method in this abstract class. And as we said earlier, an abstract method has nothing in it, so there's no static link. It basically is a no-op at that point. And it'll get replaced later by a concrete class, and that's what we're going to get to. The receiving application needs the message class, needs the abstract class, and it needs the concrete class. So it needs the what do we actually do when we receive this message? And only that concrete class is statically linked to the actor. So the code that was inside of the message class that was linking you has been moved to the concrete implementation. So you've basically separated these two. Is that clear? I've got to go over this again. If I got a good diagram here. So here, if you can visualize this, you've got these messages, and they all have their executes. Well, you create an execute for each message, and you just call it whatever you want. I call it execute message 1, execute message 2, and then the red in the middle, yellow, those are the ones that you're actually going to have in both your applications. But the light yellow, the concrete one, only has to exist in the application that does something with the message. So you can imagine you'd have maybe the other application has its own set of messages, and you'd add some more methods to your abstract class, but you'd only implement the concrete versions on the other side. So this can go both ways. You can have just one abstract class to have traffic going both ways, but then your concrete classes would just be the ones that are going to be received on that side. So they would be, let's say I had message 5, 6, 7, and 8 on another application. I would have execute messages 5, 6, 7, and 8 in my abstract class, and I'd have a different concrete class that would only have execute message 5, 6, 7, 8 in it. It wouldn't have 1, 2, 3, and 4. So you can divide that up, and I do that all the time. So it's actually not that hard. But this, if you get this slide, you get the entire presentation. This is the key, the piece of the whole thing. And I do have a demo, but if there's any questions you have on this slide, let me know. But this is the way I solve this problem. We can come back to that if we need to. All right, so here is an example of an abstract class. So again, we have our application. It has its actor, it has a message, but it has this other message that it can receive from outside of itself, and it points to that abstract execution. But then we actually inject the concrete execution into the application, so that when it really runs, it's going to use this code and not this code. So the message thinks it's calling this code, but because we've said, no, use this one, at runtime we said use this one, then it's going to run here. And this is the one that's tied to this. Now, I apologize, I'm not a UML expert by any means, so I probably use all the wrong colored arrows and dots and such, so don't take too much into this. I'm just kind of hacking this together in my head, so. But basically, that's, go ahead.
7 minutes.
Wow, man, it's taking a lot longer than my practice. All right, thank you. All right, I'm gonna speed up a little bit then, sorry guys. Oh, I gotta go show you the demo though. All right, so this is where the cool part comes in. So let's go ahead and open application 2, and in application 2, we have an increment and we have a decrement. So they both work, you can see that they're working, but if we look at the messages, we just have the increment message as part of the process, but we have a shared message where we have our decrement. Here's the decrement, and if you look at the decrement, it says, oh, just run that abstract method, ask the application what class, pull that concrete class out of the application on this abstract wire, and then run the whatever the do is, the execute here. And it has no idea what this is. This is boilerplate code here. This is what's inside every single one of my abstracted messages. But I guess the for reals thing here is this is the concrete implementation of that, and here's where we actually have that static link, and we're actually going to do this. So this is what actually happens when we run it. And if you look at the abstract version of that, you can see that it doesn't do anything. So you're statically linked only at this point, only in the concrete class, not in the abstract class. Okay, so let's make this look even cooler. So what I'm going to do here, let's see here, I've got to go back to this, next slide. All right, so we're going to have 2 applications now. So probably better to show the demo, I think, it could be more useful. Let me, I got to open up another project though to do this. One moment. Okay, so I have my caller application, and there's nothing in it, it's just a blank VI. And I open up my dependencies, I don't have any dependencies. Okay? All right, I think I got to skip too far ahead of my notes here, so I got to bounce back. All right, so in application 1, this is my my source code here. Let me just get my mouse working. I can't do this with the touchpad. I'm just going to steal all this code and drag it over here. And essentially, I'm just saying, oh, I just want application 1. I just want my simple little application here that this increments. But it's pulled in all of this extra stuff here. This process, all the things I didn't want to pull in because I put a static link to this message in there, and then that caused this to load, and that causes all these things to load. Now, if I go in to this, I believe it's this one. Read my notes, or I'm going to be wrong. Nope, it wasn't that one. It's this one. All right, so here's where I faked it by putting a static link in here just to show that if this thing needed to call another message, it would have to have a link to it. Now watch the dependencies when I get rid of that link. They go away. So I'm no longer dependent. I've removed the link, and so I don't have to load everything in the memory. And I came across this by accident because I was developing a client-server application, and I started looking at the messages I had to send between them, and I started editing one of the applications, and I realized it loaded the entire other application into the dependency tree. And I was like, oh, how the heck am I going to solve this? So that's how I came up with this solution. Okay. So does that demonstrate what the problem is clearly? Does everyone get it? Cool. Good. So why do we do this? Well, if you're developing multi-application designs, so you have more than one executable and they're going to talk to each other over the network or even across the same computer, this is how you want to do it. If you're going to use a plugin architecture and you want to be able to edit your plugins and not have to load your entire application into memory when you're editing your plugins. So you don't want to have a static dependency in the plugin on the thing that in the main application. So you can break the links this way. I do the exact same thing. I have a test architecture where I have test modules that are loaded at runtime on demand, and they have the ability to do all kinds of different things and pass data back. But because I'm using this to break the links, I can edit those in an entirely separate project, and I don't have to load in the memory my test executive just to edit my test modules. So it's very helpful in that respect. But I still have full access to everything in my main application through this abstraction. Also, if you're building reusable components that you want to use in multiple applications, and you want to provide some sort of interface to those reusable components, if you use an abstract interface like this to separate them, then you can have as many applications reuse these components as you wish. And you won't have any dependency in the reusable piece on the applications that call it. If you want to know more about that, there's an excellent presentation by Casey Lamers that he did at, I believe, at the last CLA Summit. He also did it at NI Week, and you can go online and grab it. I'm going to post this, by the way, on our forum, so you don't have to try to write that down right now. But I would highly recommend watching this video and looking at his presentation, because when it comes to reusable components, that's probably a better example. Okay, why not do it? Well, obviously it's more complicated. I mean, as you all probably can see, this definitely adds a whole other layer of complexity. You need to maintain the abstract and the concrete execution classes as messages are added or edited. So let's say you create a new message. You don't just create the message, you create the class in your abstract class, or I mean the method in your abstract class, and you create the concrete method in the concrete class. So you have to edit 3 different places. Now you only have to do this for the messages that are going across that barrier between applications. The internal messages within the application you don't need to do this for. I just want to make sure it's clear. This is just a decouple between 2 different executions. So obviously if you're writing a monolithic application, everything's already in memory anyway, so there's really no need to do this at all. It doesn't buy you anything if you're writing a single executable. So keep that in mind. And this is really for when you need to go build actors across networks. Okay. Did I do it in time? 1 minute over. Not bad. Whenever I practiced at home, I had like 20 extra minutes. I thought I was fine, but I guess I talk slower up here. Anybody want to have any questions, or or anything about all that you might be curious about, or this application? No? Okay, cool. Well, thanks for coming. Appreciate it.